Hello, class. This is MO869, Introduction to Autonomous Vehicles. Now we're going to start second module, Localization and Mapping. This is lecture 9, Introduction to Localization and Mapping. So let me start with an outline. This module starts with an introduction and then introduction to localization problem for autonomous vehicles. And then we'll move on to localization information that are available. And then we'll move on to pose-fusion algorithm. Localization in autonomous vehicles is somewhat different from other robotic systems because we are driving on structured road infrastructure. So and that poses a different problem. And let's start with what are the differences and what are the localization problems look like for autonomous driving. So when it comes to driving on these roads, we use a map. Human drivers use a map, or we could use a navigation system, and that navigation system also uses a map to guide you through the road networks. But when it comes to autonomous driving problem, this type of navigation map is usually not sufficient enough. It's not informative enough. Instead, we do need position and heading angle, accurate position and heading angle with centimeter level precision. But like I said, when we drive a car, human drivers do not need a centimeter level accuracy localization. So the first question people might ask, or you should ask yourself, is do we really have to have this high definition map, centimeter level accuracy localization and map? Well, we'll try to answer that question in the following slides. Back to human drivers, we use a course navigation map, which is enough for routing, route planning, and and sometimes avoid speed cameras. So let's go back to this question. So do we really need centimeter level localization for autonomous cars? Well, for sensor-based autonomous driving, level 2, we do not. Centimeter level localization is the biggest overhead in autonomous car technology. So one way to handle this is just not use a HD map. But level 2, low-level autonomous driving technologies will be somewhat limited in terms of its performance and safety. So, for instance, can the level 2 autonomous car understand the traffic environments only based on sensor information? Let's take a look at these scenarios. If you build autonomous vehicles that relies only on sensors, then you will have limited field of view, and you will have occlusions by surrounding objects. So you may not see all, you may not be able to see all the information that you need for driving. And sometimes misperception in various environment conditions. And of course, this is coming from using low-cost sensors. So for machine to drive, unfortunately, currently we need this overhead for us to realize autonomous driving for, let's say, level 4 or 5 autonomous vehicles, and we need to bridge this gap between human driver versus machine driver based on relying on sensor, real-time perception only tech, by looking up, by building map and using those maps so that we have better understanding about the environment, what's around the ego vehicle. What about GNSS to find my location? So we talked about map, but what about localization? Well, we can use GNSS or GPS, but when you go into this urban canyon, big cities, GNSS doesn't work well in urban canyon. So what is necessary is map-based localization. So in order for us to find the position, accurate position and orientation of the vehicle, one technique would be have the map available, and then have the perception results or sensor readings, and then match those two information to find the pose and position and orientation of the vehicle. So that's what most of the level 5 or level 4 autonomous vehicles find its positions. So let's talk a little bit more about how localization is done and how mapping is done. For localization, information fusion is absolutely necessary. Let's take a look. Why? There are various types of localization techniques, systems available, and one type of approach is dead reckoning based on internal sensors, such as odometer or IMU, inertial measurement units. Another type of localization method is landmark alignment using external sensors and map, which uses high definition map and landmark perception and GNSS information. So let's take a look at these information closer. Let's take a look at the dead reckoning approach first. Dead reckoning uses these inertial information, such as inertial measurement units. And by by computing the position and orientation based on these IMU information, which is usually accelerometer and angular speed. We need to take integral of that to compute speed and position. And then we can also use model to compute the position better. For instance, if we have, let's say we have velocity, vehicle velocity from wheel speed encoder and odometry, and then we also have gyro and angular speed information. And then, sorry for the math function is not shown properly here, but basically if we integrate these information over time, then we can compute X and Y using the vehicle model and kinematic models. When it comes to odometry, we have two types of odometry. One is odometry from motion model. We can have IMU and wheel encoder as raw sensor data, and we can use that information to compute position, and we can compute odometry basically. And then we can also do it using remote sensing, meaning sensors that are measuring outside the vehicle, such as camera and LiDAR. So there's camera-based visual odometry. There's a LiDAR-based odometry by scan matching. So the point is, odometry is available from both different sensors, but usually odometry from motion model gives you some nice features, such as shown here. The advantages are high sampling frequency, small short-term error, small environmental influence. But disadvantage is we don't know the initial position, and there may be drift error for long-term integration. So remember, I talked about this at the beginning of the semester. So when you integrate signal over time, there's always error involved with these signals, and if you have an integrator to compute position from, let's say, speed or acceleration, then drift error occurs all the time. So you need to somehow have that reset, or have a feedback mechanism to correct that long-term drift error. And we're going to talk more about that later on. Okay. And let's look at landmark alignment side a bit closer. So using these external sensors and map. So what is landmark? Recognizable features used to find your position. Let's take a look at this scene as an example. Landmarks for precise localization is needed. So by using perception sensors, we can recognize landmarks. And these landmarks should not change its position with respect to time. Otherwise, your reference is moving and it cannot be used as a landmark. And on the road, there are traffic signs, traffic lights, lane information, road surface marking, and poles. So there are these information that can be used as landmarks. So landmark based localization works as follows. So we need HD map with landmark information, and we're going to use sensors to and perception algorithm to detect these landmarks. And we're going to match those two information to find my position of the Eagle vehicle. So this is the map-based localization or landmark alignment. And then we also have GNSS, Global Navigation Satellite System, which is often called GPS, which is United States system. There's Galileo from Europe, and then there is GLONASS from Russia. And we can use these GNSS to compute the position, absolute position of the vehicle. And the GNSS principle goes as follows. So this is the trilateration technique. So for 2D example, here is the satellite position. And we're going to draw a arc with the distance information known. And then we're going to draw another arc that's coming from another satellite. And that will give us two intersecting points. And then we need third satellite to determine which of these two positions are the actual position. So in this example, this is the position of the receiver. So this was 2D example, and for 3D case, you need one more satellite to determine your position. So here's the characteristics of landmark alignment. Advantages are there's no drift error and provides absolute position data. And then there's integrated information, number of satellites, and extra information that is provided. But there are disadvantages. There's large short-term error. So if you use these, landmark alignment, then you may have large errors. Then because it requires signal processing, and computational load is significant. Usually you have relatively low sampling frequency, and your perception or map can also fail. Okay? So if you put those two, if you compare landmark alignment and dead reckoning approach, side by side, then you can see they are very much complementary. Sort of like we saw from radar camera fusion. So the idea is to fuse these two information or use both approaches together so that we can remove the disadvantages by adopting advantages of the other approach. So for instance, we can get rid of these two problems by using landmark alignment. And then by using dead reckoning, we can remove these problems also. So by fusing these two approaches and information, we can get away with problems that are present if you just stick to one of these two approaches. So we should use both information. So here's the general architecture of localization algorithm. So on the information side, we have two types of sensors, proprioceptive and exteroceptive sensors. And by using those information, we can do dead reckoning and perception. And then if we have H2 map available, then we can do pose fusion, pose estimation based on fusing these information to compute position and orientation. So let's move on to a little more detailed information for the localization information part. Today, we are going to cover up to here. And then starting next lecture, we are going to cover pose fusion algorithm. But pose fusion algorithm requires some basic review of statistics and probability and statistics and some fundamental mathematical principles before we get into these pose estimation algorithms. So we will review that, and then we'll move on to pose fusion algorithm. Okay. So let's start with dead reckoning. Dead reckoning is the process of calculating a current vehicle position by using previously determined position and advancing that position based on speed over elapsed time and course. So that's pretty, simple and intuitive approach for estimating an object. And we can actually do that using a simple differential equation and solving that differential equation. Let's say we have vehicle speed, wheel speed, and gyro information for angular speed, and we can use kinematic model. And by integrating this numerically using Euler method, we can compute angle and position. So this is the numerical integrating equation for you to compute k plus 1, which would be, let's say, current position. And to do that, you need these sensor information, and then the position and angle of the prior time step information and the sampling time. Okay. So I think that's very straightforward. But depending on which model you use, you could assume that the velocity is constant over that sampling time. Then you can use constant velocity model, and you can use these equations of motion. Again, my apologies for the broken equations. We will upload the file on KLMS. This is happening, I think, from using iPad Office app. Anyway, the point here is that depending on the model, you may be able to achieve a better accuracy. So you could use constant acceleration model. You could use constant turn rate and velocity model. Then the equations of motion becomes a little more complicated, but the prediction estimation will be more accurate. But if this sampling time is very small enough, then maybe you don't need this full more accurate kinematic models, because if it's short enough, then your approximation may be good enough. Okay, because during that sampling time, your speed and turn rate may not change significantly. So just keep that in mind, and you have different models to use. And let's take a look at HDMap side. Here's the very challenging part, and we're going to talk more about this later on. So when it comes to HDMap, people ask, is HDMap absolutely necessary, right? And my short answer is you don't have to, but if you want high level automated autonomous vehicles, then you probably need one. And even if you're not aiming for level 5 autonomy, having HDMap is always informative, very helpful, because you already know what's around you without perceiving everything in real time. So but then the problem now becomes building map and keeping them updated can be quite challenging, because this is not very the map we need for autonomous driving is more it needs to have more accurate information than the simple navigation maps, course navigation maps. So, and let's talk about types of HD map. There are two types of HD map: semantic level precise map and signal level precise map. So signal level map, HD map, as a name implies, the map is built with semantic information, whereas signal level HD map is built based on signal information. So for instance, we have this block with just all we need is size, position and size of this block, and then what this block is, right? But when it comes to signal level features, we need this in the case of 3D point cloud LiDAR case, we need this 3D point cloud information on the map. And let's say we have this perception results, and then we can match that with map. If we have sensor raw data coming in, we can match that with signal level map. So depending on which map you use, the map matching signal will also need to be changed. So let's compare these two approaches. So there are advantages and disadvantages. Semantic level map is understandable because it's semantic information and requires a small data storage, which is actually quite important when it comes to keeping this map up to date online. And then, but the downside is it becomes sensitive for map changing. Meaning that if something landmark chain moves, then because you don't have a lot of information, if one or two landmark is removed or replaced, then the localization performance can substantially drop. And you also need perception algorithm to detect the semantic information. On the other hand, if you look at signal level HD map, it's generally speaking, it's more robust for map change. Small change may be tolerable without fully updating the map. You don't need that perception algorithm, object detection, classification, semantic segmentation type of, perception algorithm. So you can build map fast. And we can automate that process as well. But the disadvantages are 3D map depth map is only valid for localization, meaning that we can't use this for motion planning module. Whereas if we have semantic HMap, we can also use it for motion planning module as well. And the biggest downside is actually signal level HMap requires large data storage, and this is quite a big disadvantage when it comes to using HD map for real world autonomous driving. So this is a LiDAR point cloud HD map. The blue points are map, and the red points are real-time LiDAR point cloud. So we can do map matching using current real-time LiDAR point cloud versus the map point cloud map information available to you. So we need to build this map based on by aggregating this LiDAR point cloud over the whole space, and then we can drive and localize the position and orientation of the vehicle. And this is another example of LiDAR mapping in Munji campus, just for illustration. And there are actually many companies working on building HD map. And here is one of them. I think it's a French company. I'm not 100% sure, but it's a mapping company in Europe. And what they do is they build this mapping vehicle. I think it's called mobile mapping vehicle, something like that, MMV, something like that. And they need to build this mapping vehicle and then drive around the town to map the whole city. And if we have to do this once and done, then maybe it's okay. But the problem is, we need to maintain and update this map. What about image camera-based mapping? This is traditional feature-based or signal level visual SLAM. This is quite famous ORB SLAM, and running on Kitty dataset. It works pretty good. It works reliably. And the ORB SLAM has this loop closure and optimization in the back end and blah 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 to do mapping and localization simultaneously. So it's a nice technology, but like I said, this is signal level, feature level mapping and localization technique, similar to LiDAR, but based on camera features, image features. Okay. And then let's move on to semantic level HD map. So this was non-semantic features, okay? So this feature does not provide you much information semantically. Instead, if we go with semantic map, then we can have these landmarks. We already have these landmarks in the world we are living in. So, and which is understandable from a human perspective. So we have these, traffic sign, lights, vertical objects, lanes, road markings, building surface, and so forth. So by using these landmarks, we can do localization, and to that we need to build landmark semantic level HD map. And let's take a look at different objects that are on the road. So let's start with lane. So we have lane. If you think about lane, there's lane geometry. There's different types of lane. There's a different color of lanes. Lane may have different width and quality to it. So lane detection also is not very trivial, especially if we have to perceive this in real time, where there's a lot of uncertainties, and then occlusions, and different lighting conditions, weather conditions. On top of that, we have these variations. So lane detection is also not that trivial, okay? And then we have barriers. We have curb, guardrails, walls, barrier geometry, and then barrier heights. So, sometimes we have, these barriers that are just, on top of the road level, but sometimes it has, vertical, height. So that can also, need to be considered when it comes to, perception algorithm, how to create, ground truth, how to model the network to be able to detect it in, 2D or 3D space, blah, blah, blah. There's building surface, it's all over the place. So it's a nice landmark. So we could use them as well. And then there's traffic sign. This is also very nice landmark because traffic sign is a very structured object, meaning that this is regulated by the position and the pattern of these traffic signs are have to follow the regulations. And those are usually available as an open source map. So we have these information, and we have traffic lights, obviously. And position of traffic lights and types and size of the traffic lights can vary, so we need to be able to detect these. And then there's also road surface marking, yeah, such as these arrows. So road marking other than the lane, there are many markings, so we need to be able to detect those in real time, and we can use that for localization as well. Vertical objects are all over the place. It's always there. So, trees, light poles, traffic sign poles. So we can. So, of course, we can use these vertical objects as a landmark, but when it comes to mapping and perception, this may not be trivial, because let's say we want to detect these using camera. What type of perception task should we use to perceive this? 2D bounding box, 3D bounding box, semantic segmentation. But we need position information of these vertical objects, right, for localization. Like I said many times, we need position 3D information for mapping and localization. And if we take a look at this also from bird's eye view perspective, from bird's eye view, these vertical objects is quite small. I mean, the volume from bird's eye view, or the area of this vertical object from bird's eye view is small, right? So how are we going to create a map with these vertical objects can also be a tricky part, right? Here's an example of here HD map with landmarks. So here's the lane, here's the barrier, here's the traffic sign and lights. And here's a illustration of how HMAP is utilized for autonomous driving. So the map is created on top of this satellite image and with lane information, and then can do localization using those landmarks. Okay. Let me pause here, and then I'll continue from here, from the next video clip. Okay. All right. So far, we talked about HD map and dead reckoning using internal sensors. And let's take a look at perception part so that we can do map matching. We already talked about perception in the first module, so I think we don't need to go through all the details. We talked about perception over 5 weeks or 6 weeks or so. So we'll just sort of review, summarize how that perception results is utilized for mapping and localization modules. So we have sensors for environment perception. We have camera, forward-facing camera. We have LiDAR. We have radar. Depending on the type of vehicle, your target platform, the sensor configuration can change. And then we haven't talked about this one in the perception module, but there's in many mass production vehicles, there's a round view monitoring system already built into it. And then there's also ultrasonic sensors around the bumpers. So using these sensors, we need to perceive the environment, which includes lane, road boundary, drivable region, traffic sign, traffic lights. All of these are static objects or environmental information. And then there's, of course, moving objects, pedestrians, cyclists, and vehicles. To give you an idea, this clip illustrates how Valeo implemented their perception algorithms and how that is deployed for localization problems. So here, like I said a minute ago, we need to do mainly two types of tasks, groups of tasks for localization. One would be semantic segmentation, but in vector space. So that includes lane, road boundary, wood markings, and then we have static object detection, traffic signs, traffic lights, vertical objects, building surfaces. We can use these information to localize the vehicle. By the way, these information obviously should be in 3D space, but oftentimes traffic signs and traffic lights are detected in image space, 2D image space. So that's not going to help when it comes to localization, because if you detect these static objects in 2D image space, then it doesn't help us when it comes to localization problem. So we need to detect these the position of these objects in order for us to use it for localization problem. I hope that's clear. So for semantic segmentation, this is just one example illustrating, what types of semantic information we need to obtain from the bird's eye view semantic segmentation task. So here we have mainly three types of objects: lane, road boundary, road surface markings. In fact, there's this drivable area as well.
Providing automakers with complete autonomy over data and hardware. Just providing automakers.
And then we have static object detection.
Providing automakers with complete autonomy over data.
As you can see in this example, you can see there's traffic signs, traffic lights, vertical objects, building surfaces. But not all of them are obtained here. So this is an example of what you would need to detect. And here is more information about what are the what type of information, what are the accuracy, association, frequency, some characteristics or properties of different sensor perception results. So here's the requirement of perception sensors for localization problem. So we want the detection performance. We want high accuracy, ability to associate perception with the landmarks. We also need synchronization, faster frequency, small data size. So these are some of the key criteria when it comes to evaluating quality of different perception sensors. So in the case of LiDAR, we have 3D point cloud. And we can draw this radar chart for different types of sensors. And as you can see here, LiDAR gives you good fast frequency rate, accuracy from highly accurate laser beam information. But then data size tend to be larger, and association where is it? With perception with landmark may not be good when it comes to point cloud. So you need to do perception. You need to perceive based on the 3D point cloud and associate with map. So 3D point cloud can be used directly, as well as their perception results can also be used for landmark matching. But the association is evaluated as relatively low because of these reasons. Hard to classify, hard to distinguish noise from the lane. And then frequency, not a problem. One of the weaknesses is the data size. There's many points from one scan, and that is large data size. Objects using LiDAR. So here, like I said, here it was 3D point cloud using the raw data directly. Here, object using LiDAR. Okay, so then the data size is much reduced. Frequency can be kept fast, and association can be improved, but accuracy may degrade after perception results. Detection here it's not it's evaluated sort of medium. That's because we also have some semantic information that we need to get for a localization problem. But when it comes to detecting moving objects, LiDAR is good. And then there's a front view, around view monitoring camera, and detecting lane. This will be will give you good data size, small data size, high frequency. Synchronization is our problem, good association, and so forth. So lane is going to be essential I would say objects, information we should use for localization. There's traffic sign. This is similar to lane, so it provides good data size, frequency, synchronization, association, performance, but then the accuracy can degrade. And then there's traffic lights. The list goes on. So if you compare these radar charts of these different information, then you can see some information is more useful than the other, and what information we have to have. For instance, we have to have lane information, and then if we can make up for the detection accuracy association part, then we are good to go for localization, and we can do that using different techniques, and we'll talk more about that later on. So the conclusion here is that the main sensor should be front or AVM camera, and then LiDAR can help. Okay. So this is it for lecture 9, and we will continue with lecture 10 right after this. Okay, thanks for your attention.